Hello students, welcome to another class on physics. In today's class, we shall be studying about projectile motion. Until the last videos, all that you studied about was one-dimensional motion. That is, the motion which is taking place either along x-axis or along y-axis or maybe along the z-axis if we are considering a three-dimensional coordinate system, the Cartesian coordinate system as we call it. But what happens when a body moves in two dimensions, when there is some motion along the x direction and also some motion along the y direction? In order to understand that, we need to understand and study about projectile motion. So here I have drawn this basic diagram. Let me just explain what is present here. This is the x-axis, the horizontal axis, and this is the vertical y-axis. This semicircular kind of curve that you're looking here, drawn in black, that is actually the path of this projectile which we are talking about. And suppose this point here, this is my origin of the coordinate system. You know, origin means the coordinates are x has a value 0, y also has a value 0. So from this origin, I am launching a projectile. A projectile can be anything. It can be a simple football, a simple cricket ball, it can be the bullet of a gun, anything can be projectile. When I am launching that projectile, I am providing it an initial velocity of v0 and I am launching it at an angle of theta with respect to the x-axis. So this projectile is inclined with respect to x-axis at this angle theta and it has got an initial velocity v0. Now, here I have marked in blue, as you can see, that this part is known as the range of the projectile. Range means the maximum horizontal distance that the projectile can cover. And this portion here, that's the maximum height to which the projectile reaches during its course of motion. Now, as you already know about this, about the resolution of vectors, like if there are two axes like this, the x and the y axis, and if I have a vector here, I can resolve it into a vertical component and a horizontal component. This I will say for my case Vx, and this I shall say Vy, as you can see here, Vy and Vx. Now what are the values of Vy and Vx? From the vector rules, therefore, Vx component will be equal to V0 cos of theta. So Vx component, that means the horizontal component of this velocity, that will be V0 times cos of the angle that it makes with the horizontal. And the vertical component Vy, that will be equal to V0 sine of theta. You already did this in the resolution of the vectors. Now, throughout our entire derivation, when we will use projectile motion, we will use the same simple equations of motion with which you are familiar. That is to say, V equals u plus at, displacement s is equal to initial displacement plus ut plus half at squared, and final velocity minus initial velocity is 2 times acceleration times displacement. These are the three equations of motion with which you are familiar, and you also know how they are derived. And it is these three simple equations which we shall be using for derivation of the projectile motion. Now, one thing that you need to know clearly here, that when throughout the motion, the course of the motion, the only acceleration that the body or the projectile experiences is the acceleration in the downward direction due to gravity. Gravity pulls this projectile in the downward direction at all the times, and since gravity acts vertically downwards, so acceleration is only taking place along the y-axis. Along this x-axis there is no acceleration. So when the body is moving along the x-axis, it's as if a motion with uniform velocity, but the motion along the y-axis is a motion with uniform acceleration or changing velocity. And the fun part about this projectile motion is that you can treat this as if they are two different one-dimensional motion, as if one motion is taking place in the horizontal direction at all times and another motion is taking place in the vertical direction at all times. You can treat both of them separately, and yet magically you can come down to the final equation explaining this projectile motion. At any instant of time, how does the equation would look like in terms of velocity? So if this is the curve, initially it has a horizontal velocity Vx and a vertical velocity Vy. At some another point, the horizontal velocity remains constant. Hence I have drawn the vectors to be roughly of the same size because the magnitudes remain constant. But now the vertical velocity, that is slowly decreasing. At this point, horizontal velocity is again constant, vertical velocity is even smaller. At the topmost point, there is only horizontal velocity, no vertical velocity, because now it cannot rise any further than this. So at the highest point, we have been doing this since earlier days, that for any kind of motion under gravity, at the highest point you have the zero velocity. But that was in free fall and that was a one-dimensional motion. Here it's a 2D motion, so though the vertical component is zero, since the horizontal component is still present, the motion will continue. And now gravity will be pulling it downwards. So what will happen at this point? Horizontal component still remaining the same, but vertical component slowly increasing in the downward direction. So this is how the motion looks like. And since you know about resultant vectors, see at any point there are two vectors acting. The final velocity vector along the y-axis and the velocity vector along the x-axis. And it is the resultant which leads to this projectile motion. So if these two are the two edges of the parallelogram, resultant will be the diagonal. And you see clearly that is how the motion is taking place. Having dealt with that, we will now come into the conditions. And as I said, we will treat this as two different one-dimensional motions, one taking place along the x-axis, the other taking place along the y-axis. That is how we shall be treating this. So first of all, consider along the x direction. Along the x direction, initially, that is at time t equal to 0, that is when motion is yet to start. At that time, what is the displacement of the body? The initial displacement? It is 0 because it's starting from origin, so there is no initial displacement along the x-axis. What is the initial velocity v0 along the x-axis? This is not 0, it's naught, which signifies initial conditions along the x-axis. That is nothing but what we wrote down here, v0 cos theta. And what is the acceleration that is taking place along the x-axis? Well, there is no acceleration along the x-axis. Acceleration is only taking place along the y-axis. At the same time, that is in the initial conditions, that is when time is 0, what is happening along y direction? Well, the initial displacement along y direction is also 0. It's starting from origin. The initial velocity along the y direction, what will be v? V is u plus at. So u is my v0 sin theta plus at. And what is acceleration? Acceleration is equal to minus of g, because here this is my positive y-axis and gravity is acting downwards. So acceleration is the negative of gravity if we take sign into consideration. Therefore, in place of a, we will put minus g. So this becomes minus g times t. But we are considering the initial condition t equal to 0. So if I put t equal to 0, this term, that does not exist any longer. So vy initial is simply v0 sin theta. And what about the acceleration along the y-axis? It is again minus g. This is the only place they are different. Here the acceleration was 0, here it's minus of g. Now suppose that the body has moved for some time. Say the body has been in motion for a time t. Now what will happen to these values? What will be now displacement x along this direction? Well, the displacement will be the velocity along the horizontal direction, that is equal to my v0 cos of theta times the time for which it is moving, because x is displacement s is s naught, which is my x naught 0, plus ut, u is along x axis v naught cos theta times t, and plus half at squared, acceleration is 0, so this is what simply x is. What about the velocity along the x direction? Using this equation, v equals u plus at, it is simply v naught cos theta, because again acceleration is 0 and the acceleration that remains 0. Certain things will change for the y-axis. For y-axis, now the displacement y, what is it equal to? Y equal to y naught, which is 0, plus ut. U is this one, the initial velocity. So it is v0 sin theta t, plus half at squared, that will be becoming minus half gt squared. Because now it is not initial condition any longer, so t is not 0, so this term will exist. The velocity of y from this equation is v0 sin theta plus at, that means minus gt. And finally, acceleration along y, that remains constant as minus g. So as you can see clearly, we have depicted the conditions that the projectile is experiencing at two different instants of time for x-axis and y-axis separately. This is the initial conditions, these are the condition at any arbitrary time t. We put the value of time t, we get the results. And as I said, we can treat this motion completely as if it's happening in two different one-dimensional motion, one along x-axis, the other along y-axis. Now we shall attempt to find out the equation of motion for the projectile. Okay, so let us look at this equation. X equal to v naught cos theta t. From here, if I make time to be the subject, time becomes x divided by v naught cos theta. I get this from this equation. Now I will substitute this value of time in this equation. Y equal to therefore v0 sin theta times t, which is x by v0 cos theta, minus half gt squared, so minus half g t squared, that is x squared by v0 squared cos squared theta. Alright, this gets cancelled, x sin by cos is tan theta, minus gx squared by 2 v0 squared cos squared theta. So what is the final equation of motion for a projectile? Y equal to x tan theta minus gx squared divided by 2 v0 squared cos squared theta. This is the equation of motion for a projectile. Y equals x tan theta minus gx squared by 2 v0 squared cos squared theta. So what can we see here? We see that the equation of motion, it obviously depends on theta. There are two theta terms, one is tan of theta, other cos of theta. So at what angle you launch the projectile, that matters. Secondly, the thing that matters is what's the value of acceleration due to gravity at that place. The equation of motion on Earth will be quite different from that on Moon, where value of g is different. And obviously it depends on v0, that is the initial velocity with which you launch the projectile. Now at this portion, if you look at the board, you can see almost the entire story of the projectile, starting from the diagram to the equations we have used, the initial conditions, and what we have achieved finally. So at this point, if you want, you can pause and take just a screenshot of this thing, and then if you note it down, it will be very useful for your derivations. And because I shall be rubbing this as I move on to the next portion. So now that we have this equation, what can we infer from this equation? What does this equation look like? If you look at this equation, the highest power of y here is 1 and the highest power of x is 2. So whenever you have two variables in equation where one is linear like this one and the other is quadratic, like this one. Those type of equations come under the broad class of what we call parabolas. So parabolas have got this general equation like y equal to some constant times x squared, or x equal to some constant times y squared. And how does the graph look like? So if this is my y and the x axis, for y equal to some constant time x squared, the graph looks something like this. This is for y equal to kx squared. And if it is x equal to some ky squared, the graph looks like this. So in our case, it's y depending on x squared, so our graph is this one. But you will say that the motion is like this, then graph is like this. What's happening? What is happening is, like, if you rotate this graph by 180 degree, what will happen? It will look like this. You have rotated this thing by 180 degree, and if you look at this portion now, this is exactly what's happening here. Why did we have to rotate it by 180 degree? Because this is my positive y and gravity is acting downwards, -t. But in real life, this does not happen. In real life, gravity acts in the downward direction. So for that case, this is how the graph looks like. This one is known as projectile motion, and this is the nature of the projectile motion equation. It's a parabola.